Okay, now let's take a look at logarithms, and after that then we'll take a look at how logarithms are used with sound intensity. So there are two different types of logarithms. One is called a base 10 logarithm, and the other is a natural logarithm. If you look on your calculator, and I know you have different versions of calculators, but what you probably will find on your calculator is there will be a button labeled LOG. And the button LOG is for doing calculations in a base 10 logarithm. And then you might also, next to it, you'll see a button labeled LN, and that is used for natural logarithms. So we're not going to use natural logarithms. Sound intensities will be based on the base 10 logarithm. But let's just take a minute and talk about natural logarithms. So natural logarithms would be used for natural processes. For example, a natural logarithm could be used to help describe maybe the growth and decay of bacteria in a petri dish, or the growth and decay of any kind of population, more biological type of processes. And whereas the base 10 logarithm uses a base 10, the natural logarithm is not a neat and clean number like that. In fact, you can even see what it is. Now on your calculator, again, you'll see the LOG button and the LN button. Now just above it, there should be a shift function just above it. On mine, the shift function above the LOG key is 10 to the x, and just above the natural log button, it should be e to the x. So we can find out what this base e is. So if you take your calculator and enter the number 1, and then activate this e to the x key, so you might have to use your shift key, then you should have on your display what that base is. E is 2.71828, and then it goes ahead and continues. So that's why it's an odd kind of number, because it's a natural biological type of process. So it's just not a neat and clean whole number like we're used to. Okay, but we're not going to use natural logarithms. We'll use base 10. All right, now the reason that the function above the LOG key is 10 to the x, because log and 10 to the x tend to be in their inverse function. And we'll see how you would use that. So when you take the log of a number, so anyway, let me back up a little bit. So the reason we're going to be using logarithms, because in the last part we said that the difference between the pain threshold and the hearing threshold is 1 trillion times in terms of sound intensity. And that's a vast, vast range of intensities. So what the logarithm will do for us, if we take the logarithm of those numbers, it kind of squeezes those numbers down into a more manageable set of numbers. So it kind of compresses that range of numbers. It may make it easier to express and to use. So let's see how this works. So when you take the log of a number, then really what you're doing is you're trying to figure out what exponent of the base 10 will result in that number. So let's take a look at an example. Let's take the number 10. If you were to take the log of 10, the question you're trying to answer is, what exponent of base 10 will result in the number 10. So if you take your calculator, enter the number 10, and then push your LOG button, you should get the number 1. And what that means is, so let's say, okay, so the log of 10 equals 1. That means that what the question you're trying to answer is 10 to what exponent equals 10? So obviously 10 to the first power equals 10. But what you've done in the process, remember I said that the base 10 log is used to take a big set of numbers and compress them down. What you've done by taking the log of 10 is you've compressed the number 10 down to the number 1. So you've already seen some compression there. You've taken that and made it smaller. Let's look at a few more examples. What about the number 100? If you took the log of 100, again you're trying to answer the question, what exponent of the base, what exponent of 10 will give you the number 100? Well, it's 2, but let's confirm that with our calculator. So enter the number 2, push the log button. Excuse me, I did it. I forget what I just said. We're taking the log of 100. So you enter 100, and then you push the log button, and you should get the number 2. So log of 100 equals 2, which means, and really what that's telling you is 10 to the second power equals 10 times 10, or 100. So once again, you've taken a big number, 100, and by taking the log of it, you've compressed it down into a small number. We'll do one last example. Log of 1,000. So go ahead and punch in 1,000, push the log button, and you see you'll get the number 3. Because 10 to the third power equals 1,000. So that's just a quick example of how the log function works mathematically. And as I said, the function that's listed, the shift function that's listed above the log key 10 to the x, just kind of reverses that. So for instance, let's use this example. If you enter the number 3 in your calculator, and then you activate that 10 to the x function with your shift key, log button, it tells you 1,000. Basically, it's just reversing the process and says 10 to the third power is 1,000. So other than for sound intensity, where might the logarithm scale be used? Well, there's one common example that you often read about in the news, and that would be the Richter scale for earthquakes. That scale was developed by a university professor named Richter back in the 1930s, and as a way of expressing the intensity of earthquakes. Because just like sound intensities, the range of intensities of earthquakes, from very mild earthquakes to very big earthquakes, is vast. Huge differences between, say, a 9.0 on the Richter scale earthquake and one that's maybe 1 or 2. So as a way of, again, trying to compress, and in earthquakes we're talking about the energy of an earthquake. So in order to take that vast range of numbers and squeeze them down into a more manageable and expressible format, the base 10 logarithm is used. So let's take an example of that. I mean, every couple of months you'll read in the newspaper about an earthquake in California that's maybe 6 on the Richter scale. So let's say you have a 6.0 earthquake. And then a couple times a year you might see one that's maybe 7. Maybe you'll see one over in Japan that reads 7 7.0 on the Richter scale. So the question is, what is the difference in energy or intensity of those earthquakes? Well, what we're seeing expressed there is the exponent of 10. This is based on base 10 log. So the difference between a 6 and a 7 is 1 exponent of 10. So in other words, a 6 on the Richter scale is 10 times more intense than a 7.0, because the difference between 6 and 7 is 1 power of 10. So there really is a vast difference between a 7.0 earthquake and a 6.0 earthquake. Now, as an even more another example would be back in 2004. You remember the big earthquake at Sumatra that caused the big tsunami out in the Indian Ocean. So that one was about a 9.0 in Sumatra. They don't happen very often. So what is the difference in energy level or intensity between a 6.0, which we occasionally see, and a 9.0 that we rarely see? Well, the difference is 3 powers of 10, 10 to the third, or 1,000. So the earthquake in Sumatra was 1,000 times more powerful than what we would consider a rather strong earthquake in California at a 6. Again, you can see it helps in terms of being able to express those numbers, because there's such vast differences between a mild and a strong earthquake. All right, so now let's take a quick look at how we're going to use the log scale in expressing intensities. Okay, so we already talked about intensity We talked about intensity of a sound as power divided by area, and that equals watt, and the units of watts per square meter. Now, in terms of how we will actually express the loudness of a sound, we're not going to actually use intensity. We're going to use something called intensity level. So this is intensity. So we're defining intensity and intensity level differently. So intensity level is going to be a comparison between the intensity of a sound and the intensity of the hearing threshold. So we're going to use the Greek letter beta, and that's going to be equal to 10 It's going to be equal to 10 times the log, this is the base 10 log, of the intensity of a sound in watts per square meter divided by the hearing threshold. And that's always the same. We defined that previously. Now, what you're going to get out of this equation is the units of decibels. And you may have heard of that unit before to express the loudness of a sound. Now, if we didn't have the factor 10 in the equation, you would actually be getting what's called bells, B-E-L-S. But by putting in the factor of 10 here, there are 10 decibels for every bell. So we're going to be getting actually decibels out of this equation. So in order to calculate decibels, you need to know the intensity of a sound in watts per square meter, and we already know the hearing threshold is 1 times 10 to the minus 12 watts per square meter, and it will always be that number because that's the way it's defined. Okay, in the next part we'll work through some example problems of how you would actually do this calculation.